the last part of Unit 2 is about symbol tables and about binary search trees, which arguably is the most useful and most fundamental of all those data structures we covered here. And so I think it's particularly useful to know about. It's also just a beautiful piece of theory that this works. I mean, you get used to it so much that maybe it loses all the marvel and wonder, but it's quite a feat that it's possible. But let's first talk about the abstract data type that comes with it. I asked you this fun question. Let me switch back to it briefly. So you're not young enough, or at least old-fashioned enough, to have used a physical printed dictionary. Of course, the reason why I asked about this is, how do you find a word in a dictionary? And we'll come back to that. So first of all, let's get some terminology straight out of the way. So we have symbol tables. That's the way I call them here, and that's the way they're called in the algorithms book, the red book that I recommended you to read along for this unit if you haven't had this in an undergrad course. But there are many other names for the same thing. It's important just to know that these are the same, okay? So symbol table, sometimes called dictionary, including in Python. In Java, it's called a map. It's sometimes also called associative array, or key value store is essentially the same. Often people mean a distributed database instead of something on a local computer, but it's by the API the same thing. So the key thing we can do with this, and this is dynamic, you can change it over time. You can put a mapping into this symbol table where you associate a value v with a key k. And in Python, you would just write it like this for a dictionary. That is also why it's called associative array sometimes, because it looks by the syntax like an array, but the thing you put into the square brackets is not a number, not an index or an offset, but some arbitrary object. Then if you have a key, you can look up what the value is that's associated with this. And symbol tables are fundamentally single valued. So every key is associated with one value, or maybe no value if it's not contained. But if you call put several times with the same key, it will just overwrite the previous mapping. You can also remove a key and its mapping again, and you can check whether something contains a given key, whether a dictionary or a symbol table contains a key. Of course, you could also check what get returns, and if that says, I don't have a mapping for that key, you also get the same answer as for contains. That's just to make it more readable. As I said, it's a fundamental building block for pretty much. I can't imagine a program that doesn't in some way use one of these data structures, indirectly at least. Very fundamental. And okay, I don't think I know a programming language that doesn't have a library that contains a symbol table in one form or another. Now, there are many esoteric programming languages. Maybe there is one out there, but not. If it's in practical use for real-world problems, it will have a symbol table. It's useful to make the distinction between symbol tables and mathematical functions, because they're, in a way, very similar. Both, you give a value and then you get a mapping. You put a key in and get a value out. For a mathematical function, we say also you just put one key in and get another key out. So they look a bit similar. But the big difference is, if we think of mathematical objects, we think of them as immutable. These are values that don't change. If you take the number 5 and add 1, it's no longer the same number 5. It becomes a value 6, but the 5 isn't changed. Whereas data structures in computer science, and specifically our symbol tables, we assume that they can change. So you can change the mapping of a key. So you can think of it as a dynamic function or dynamic mapping if you want. Just want to get that, make that clear. So it has this similarity to functions, but changing over time is the difference. So we have a new abstract data type, the symbol table. How can we implement it? What kind of data structures are there to implement it? Now let's look at the simplest possible ways first again. We could use an unordered list, say a linked list. It shouldn't matter that much. I can hear me a lot. Is that still loud enough? No complaints either way, so I'll take it as a yes until someone complains. Let's take an unordered linked list, and when we put a new key value mapping in, we just stuff it at the end. That's fast. Yep. Oh, unordered here just means I don't care about the order. It's in contrast to the other option that will come. So what it means is I keep you say put hello 5. Then I'll just create a new entry in my list that has the key and has the value. And it's somehow linked with pointers. So if you do another put a 0, then I'll just add another thing at the end of this linked list. And there's no specific order maintained in the list. The newest thing is just at the end. That's the way it's meant. It's not sorted. It's also not random. We don't deliberately randomize it. It's just the order in which it is inserted. But unordered here stresses the fact that we don't specifically impose an order. That's all it says. So you can't guarantee anything. Which means put is fast because you just put it at the end of your list. But if you want to find the mapping for a key, the best thing you can do is just go through all the mappings, check with each key, is this the key that I'm looking up? If no, you keep going. If yes, you return the mapping that you found. But actually, even in that case, you have to go through the entire list and check if there's another mapping with the same key, because you should return the newest one. So there's a second problem lurking. This might grow over time, even if you just put in the new key. So you might need some cleanup calls and so on. I'm not even listing the details here because this is so slow, it's not interesting. If that's the best we could do, symbol tables wouldn't be a thing. The other alternative that we have is using some sorted thing. And I put here again sorted linked list to emphasize this, because if we want a sorted list, but we want to insert something in the middle, we can't really use an array. We've had this problem last time, we discussed it in a bit. So you can append to an array using this doubling array trick, but you still cannot insert in the middle of an array without moving all the elements. So either way we do it, either linked list or an array will actually get us linear time worst case for put, even if we know where we want to go, because we have some fast way to find it, it doesn't help. If we use a linked list, then certainly also get is just as slow as before. The sortedness didn't really help us there at all. Right, sorted here means sorted by key. Although, because it didn't help here at all, it doesn't actually matter. But going forward, sorted will always mean by keys. But I'll comment on that again. So the strange observation here seems, at first, sortedness doesn't help us. Because just a simple way, maintain something like an array where you can quickly access elements by index, but also insert in the middle. That's already a tricky problem that we haven't really solved so far. But we'll see binary search trees actually solve that. Yeah, that's the point. It would help us if we could somehow jump into the middle, right? I know you all know this, so let me move ahead. There's, of course, this thing called binary search. And I asked you about the physical dictionaries because of that. How do you find a word in a dictionary? You do something like a human-guided binary search. I guess no human does exactly binary search, like opening the book in the middle, checking if you're to the left or to the right of the current page. We do something with the starting letters, but it's not too dissimilar. But let's, to be self-contained, let's briefly go through this more formally. So if we have somehow an array of sorted elements, and here I'm only listing the keys. There is a second array that associates the values with those if you want. We'll ignore that for now, as in the case of the heaps, because it doesn't actually make the data structure more interesting. So here we have these keys in sorted order. Let's try to search for some key, say 69. So what binary search would do is you jump into the middle. That's this M. Index M is basically the middle between L and M, somehow rounded if it's between two. So here we would have checked 63. And 63 is less than 69. What that means, because of the sortedness, is everything that's left of 63, including 63 itself, is excluded. If 69 is in the array, it is not in the left half, because all of those are too small. That's the key trick of binary search. And then the rest is just putting this into a nice recursive algorithm that nails down the remaining range of the array. So after this, we can update L to the position to the right of that. Then we get a new M, so we can again do one comparison with that. Now that's bigger than 69, so we know the 80 and everything to the right is excluded. If 69 is in the array, it is not in the right part of this, in the right half of the right half. So we narrow it down further. We do another check, 77, still too big, so we exclude again these two. And then we've narrowed it down to a single value that we can just check. And in this case, of course, we find the 69. That's binary search. I hope this wasn't new for anyone. I hope also it wasn't too boring for anyone. So what we do is, in each step, we roughly halve the remaining number of elements, plus minus 1, because we can't, if it's an odd number, we can sometimes not work our way around it. But if you do the math a bit more careful, the number of comparisons, so the number of times you have to check something against your key that you're looking for, is at most log n, the number of things you have, rounded down plus 1. Okay? That's the number of times you have to cut n in half before you're at 1, by and large, and then the plus minus 1s, you have to do the math. So that's good. That's great, actually, right? Log n is very small compared to n. And all we previously had linear time get or put. So that's great. It comes with this restriction or this caveat. What we needed to do binary search is being able to jump into the middle of the array. And insofar, sortedness helped us for this. But sortedness is a problem if you want to insert into this array and it's still an array. So far, all we've seen was either random access with an array, where we can jump at any position, or quick insertions in the middle, but then it's a linked list and we can't use random access, as I called it here. So random access is maybe a slight misnomer. It should be called fast access by index. But that's why we call RAM. RAM, it's the random access memory, where you can do accesses by index fast, as opposed to old magnetic tape, right? This also existed. So it's maybe not the greatest term, but it's so established that I kept it. What's meant is you can jump to position 17 in one go. Good. Everyone with me? So we'd like to have this fast search, but we can't really do it with an array.